Okay, ready. So, last lecture of the course, and the plan today, we will speak about um, PL condition and how it guarantees fast convergence of stochastic gradient descent. And from our theory, we get extra bonus. We will show that when we train neural net, we obtain weights from some complexity class with small Rademacher complexity. Hello, welcome. So, okay, let me just repeat because of 50% increase of, so there is one person online. So it's, um, so the goal today, I will speak about PL condition, about fast convergence, lazy training, so fast convergence of neural nets, and I also will explain why, what we started last time, why update of weight is relatively small when training converges. No, yeah. Um, and this is good news because we know that when the weight vector is small in a linear class, then Rademacher complexity is small. And then we had a system to bound the Rademacher complexity of neural net, and just like we look at a bunch of linear functions, and we could bound the Rademacher complexity by the size of the weight. But now we have a small change from a random weight vector. So after we fix the random start point, we are in a small class, and we also know that adding something to classifier fixed thing doesn't change the Rademacher complexity. So the lazy training is good news because it keeps Rademacher complexity of neural net small and then gives a small generalization error. But there is condition, gradient descent must converge fast. Okay, so now we will, so the whole plan is quite technical. And so I will explain all of the parts, and then the parts I didn't put them together because it's just like 2 pages of calculations and I didn't have time to type them, but also it's a bit boring. So I think if everyone understands the parts, so we will have a parameter k, which is the width of the network. And so you will see k is constant, or so something is constant, proportional to square root of k, or linear to k. And that are just the things you need to track. To under, but then there is a bunch of parameters. So, but I will copy paste like the full statement of Belkin paper into the notes. And then just say, okay, if you and also in the notes there is a little problem on the second section. I mean, everything is correct, just I did it in a stupid way, and I realize it now. So I will rewrite a little bit after the lecture. So by the evening, everything should be okay. Yes, so this is enough, blah, blah. Let us start with where we ended last time. So the general plan was to say that gradients are stable during training. And in each training step, we are adding a linear combination of gradients, right? And then we said that why gradients are stable, it's because Hessian of loss function well, we already understood that Hessian of input-output of neural net was small. So if we fix one input and we look to the function that maps parameters to the output, we get a real function, and we understood that this Hessian of this function is small. And that means that the gradient is stable if you change the point not too much. So that we did in the end of previous lecture. And in the seminar, you calculated Hessian of a neural net with one layer of hidden weights. But so this Hessian, the same calculation propagates during several layers. But each time you go to the next layer, there are some multipliers that depend on Lipschitz constant and so on. So if you have a constant number of layers, everything we say also works for constant number of layers. But then again, there is a technical mess, so I will just refer to one hidden layer, nets with one hidden layer. Okay, let's now recall what we said. So we had the gradient. So let's first recall notation. So we have a vector function f. So it takes n parameters, and this number of parameters, and it output n values. And so it goes like w is mapped to this vector f x1 w till f xn w. So f is the output of the neural net or whatever system you're considering. So we have training points x1 till xn, and so when we fix the vector w, we have a list of outputs, and then the loss of w is just the f of w, this 1/2 of the squared norm. And here y is the vector containing all values of the training set. Okay, and then the gradient. So when we take square loss, then the gradient in w, so gradient in LW is equal to, so how do I write it? So we had this notation, d of L, d of f, of w times f of w minus 1. This doesn't work, so something is wrong. So what is this d operator? You remember? So yeah, Jacobian, yeah. So here the dimension don't work. So I need to take the transpose of the Jacobian. So the second coordinate, the rows are the gradients of each of the functions f. Okay, so here we see that gradient of L is linear combination of gradients of each f, small f with a fixed coordinate. Okay, so this, and now let us see that there is exponentially fast convergence of the solution under gradient descent. And so in gradient descent, we say that Wt plus 1 is equal to Wt minus the learning rate eta minus gradient of L of Wt. And so let's change the marker. So we have that's right. On the other side, minus. So this is equal to minus eta of what we have here, WF transposed minus y. And now let us see how the loss changes. So I claim that the loss will decrease under some condition, will decrease exponentially fast. So loss sorry, so we converge exponentially fast to a certain solution. So let us look what is f of wt plus 1 minus f of wt. So let us use a linear approximation of f to estimate this loss. So I'm just telling what is the general idea. So that will be equal to df is df of w t times the update of the weights wt plus 1 minus wt. And so here this is equal to proportional to the gradient. So I plug in this. So we have df of wt times, so minus eta df of wt transpose times fw minus y. Okay, and this is good news. So let us call this difference the vector u. And so let us say that ut.
Could you please repeat why what we did like last thing?
Yeah. So here we have the difference of here.
Yeah.
So I just copy this.
Oh, okay.
So not much is happening, but this is very good news. So there is a simple observation now. So let us use vector u, ut, or yeah, why not? Ut equal to f w minus y t. And then we have nice exponential convergence. So we have that ut plus 1 is equal to ut minus eta df of wt df wt transposed times ut. Or one more. So it is equal to ut 1 minus eta. And so here, this thing, what we see here, we will call the tangent kernel of f. So we say that k of wt is equal to the f of wt, the f of wt transposed. And so what we have here is, oh, this is important. So let us rewrite it in a nice place. So we conclude that ut plus 1 is equal to 1 minus eta k of wt ut. So ut is the difference, how far we are from converging. And now there is an important conclusion. So if eigenvalue of k, min eigenvalue of k is positive, then we have exponential fast convergence of gradient descent. So this is cool result. And moreover, we can relate. So we know that f so will converge exponentially fast. So the total update of values of f, so all the difference in gradient steps, it will be bounded by a constant. But the difference of f, because we have linear network, is proportional to the difference of w's. And so here we see that w's will like go very fast to the solution, almost in a straight line. So it curves around it. But since the steps decrease geometrically fast, the detour it makes from like going directly to the solution is bounded by a constant. And so the constant from the geometric expansion. And this is what we will just say in half of the lecture. So we will bound the difference in W. And this is good news because we want to prove that we have stable gradients, that df is stable. We already know the Hessian is small. We also know that we only care about the values of W near our start point. And so we know that if we stay near the start point, the Hessian is small, and if the Hessian is small, then the gradients are stable and we stay near the start point. So there is a recursive argument there. Because Hessian is small, we are in the linear approximation, which guarantees fast convergence and so on. But everything depends on minimum eigenvalue of tangent kernel being positive. So it only works under this assumption. And here is the whole, where in practice, this theory is kind of neither false nor true. So where it's not completely false, but also not completely true. But we also need only a weaker assumption. We need that y, so the difference of f0 and y is in the span with large eigenvalues. And so there is paper by Aurora, I will add the reference to the notes, where a little experiment is done on this data set and CFAR, that they're the famous data set, like many papers use them. And so they observe that NTK has positive eigenvalues, but the solution, the vector y, the answer on it's a classification task, multi-class. Okay, there are some details, but classification task, the vector y lies indeed is mostly a linear combination of the big eigenvalues of k. So they have, yeah, I actually should have started with this. So what they observe is that, let us look to the loss in gradient descent. And let us use gradient descent with correct labels. And then they indeed find that the loss decreases very fast in number of iterations. So they didn't use mini-batch, just simple gradient descent. And so when they use labels from training set, so the true labels, but when they use random labels, they notice that gradient descent converges much slower. And so they connect this to k. And then they can also, they choose that they calculate all the eigenvalues from k, and they choose as labels the eigenvector of k with smallest eigenvalue. So they choose the labels adversarially. And then they choose, they see that there is almost no decrease. There is decrease, but extremely slow. And so this linear behavior is kind of experimentally verified. Of course, if you use random labels, then you cannot expect much generalization error. And so they also propose a bound for the Rademacher complexity, but it's one that's a bit hard to prove. So they say if y is the label vector, then they say that what was it again? Okay, I remember. Okay, so they use the letter H, so that's why I'm confused. I confused with Hessian. So they say that check the paper. So they bound Rademacher complexity by, yeah. So by this function. So here we have NTK in random point, and here there are the label vectors. So, but this bound, it's a bit difficult to prove. I will skip it for this lecture. There is not enough time. And so let us first focus on this PL condition and why K remains stable for this lecture. Okay, so now you understand the plan. And this we already did. So we discussed the plan in previous lecture, like general plan to prove. So our general plan was. So there was a simplified plan that I explained previous lecture. It has two steps. So previous lecture we will say that gradient of f xi w is well, sorry, what did we say? The plan was to prove that h of f in W is small. And then to prove that updates of the weight factor W minus W0 or W1 for the first step, no, W0 is small. So bounded by O of 1. So O of 1 independent of the width. So the parameter here will be the width. And we prove that Hessian goes down by order 1 over K. So we have network with, so this achieved in previous seminar, right? And then we conclude that the gradient, then we said that there was a lemma also in the seminar, f of W prime minus gradient of f. So I fixed x. Because W is smaller than W minus W prime times maximum of gradient. HF of W, and here W was in the segment from W to W prime. So now we will refine this plan a little bit. So, oh, no, this is our plan. Except that here we will bound the difference of min eigenvalues of NTK. Because in this exponential decrease, what we actually use here is the min eigenvalue of NTK. This will guarantee that the norm of UT decreases exponentially fast. So we only need min eigenvalue in our previous reasoning. So actually, it's an important step. So I already deleted the calculation, but you can just look here. So what happens to the norm of UT? And so norm of UT is bounded, UT plus 1 is bounded by 1 minus eta lambda min of K omega T times norm of UT, right? It's clear because this is a max eigenvalue of this matrix. Okay, so yeah, so then we will make a relation between gradients. Actually, I don't remember at the moment how it is done. But anyway, for the colloquium, only the intermediate step, these two steps are asked. Or I think even only this step, which is the main step. Like proving that Hessian is small is kind of routine calculation. So you can do it since the first year where you learned about derivative and chain rule. So here is our main task. Okay, so Hessian has small norm. And so the first thing we will do is prove a very old theorem about convex optimization. And so the guys are Polyak and Lojasevic, and they have some important criteria for convergence of loss that follows the previous reasoning in an approximate sense. So all what I said is I linearize the network, but we don't have a linear network. And so of course we won't be speaking about functions, but the same arguments hold under PL condition. And so so the claim is that if so let me. So what we'll be using is that we will use that a gradient is relatively small, big in gradient descent. So if in each step of gradient descent, we have that this is bigger than mu L of WT in each gradient descent step, then we also have exponential fast reduction of error. So, so the condition is that so if this holds, in each gradient descent step, wait, eta, and so we assume L is bigger than 0, and L is 1 over eta smooth. So that means that Hessian, and so max eigenvalue of Hessian is bounded by 1 over eta. Then we have exponential fast convergence. So this is a more finer statement of previous for nonlinear networks. So then LWT is smaller than 1 minus mu eta to the power t LW0. So it's from 1963. So Polyak, Lojasevic, so some Polish people. Okay, let's make this. I hope. No, not as in yen. This is their theorem. Okay, and the proof is not too hard. So proof is just saying that yeah, so just by Taylor approximation from L, and if we fit everything from gradient, if we fill in everything, we nicely get this result. So we will prove it by induction. And so we will prove that LWD is smaller than 1 minus of D plus 1, smaller than 1 minus eta L of WT. Okay, so let us start. So we use Taylor approximation around WT. So we know that this is equal to WT plus gradient of L. Let me write it differently. WT plus 1 minus WT times gradient of L and WT plus Hessian. So then we know that there exists some W tilde in the interval of WT plus 1. And so that here we add 1/2 WT plus 1 minus WT Hessian of F and W tilde WT plus 1 minus WT. And here we need to take the transpose. Okay, so a lot of calculations. And now we substitute. So we know that the update is proportional to the gradient. And then we have something nice. So here we have 2 times the same thing. And we can bound this by smoothness. We know that this value will be 1 over eta. So that is insert everything we know, and then we are basically done. So it is equal to LWT plus, here we have well, minus eta times gradient of L and WT, just by definition of gradient descent, times gradient of L and WT, plus, so now let us upper bound this term using 1 over eta smoothness. So we have here 1 over 2 eta, and here we have the same thing again. So norm of LWT squared. And this is good news because the condition here, PL condition, this is called PL condition, this thing. Oh, it fits very nicely. And so I can, so let us get, remove this and change the sign here. Right? And now PL condition says that here we have negative thing. So we, for an upper bound, we replace it by something smaller. So we have L of WT minus 1 over 2 eta times mu times L over WT. And so we are finished. So we have proven this. Sorry, there is a 1/2 here in the front of the gradient, so I should not write it. So
And why did we change the sign before one?
yeah, so I deleted. So here we have the norm of gradient squared, but with minus eta. And here we had plus 1/2 over eta norm squared.
Oh, okay.
So yeah, I dropped. So together it's minus 1/2. And then I was lazy. Yeah. Okay. So, or saving time. But I made a little mistake because I also need the 1/2 when I do this. So I should not write the 1/2 here. And I made another mistake because the update of WT here has a factor eta. So here we have factor eta squared. So now it works. And so I don't have 1 over eta here, I have eta here. And so it's precisely this thing. Or I can write 1 over eta eta squared. Okay, so well, cool result. So we just have this thing. But there is a little detail. So we need 1 over eta smoothness of L, and we need to guarantee this condition. So we have 2 tasks when we want to apply this to a neural net. Okay, and so we will then use a refinement of this theorem. Okay, so where do we use the PL condition? So only in the gradient descent, and we need eta smoothness in the trajectory between the updates. So only eta smoothness is used on W tilde between these 2 points, because it's only used to bound this thing here. Okay, so now I will write an X theorem that we will prove. So I can delete the proof, right? So it's not so easy. So you don't need to worry about, like, if you have 10 minutes, you can always reinvent it. but I cannot do it of 9 in the morning. But, so now we will prove a refined version of this. So for the squared loss. So here we didn't use anything about the loss it's for, but now we need the squared loss. So theorem says provides the same convergence speed, but under weaker conditions. But we will use squared loss. So the theorem is that so we will only need smoothness locally, and we will express it. So using smoothness of f. So we assume that f is C Lipschitz. Okay, sorry, I said it again. So our main trouble is this PL condition. It's generally not true in a network everywhere, but it is true in a local area around a random weight, W. And so now I will make a refinement where I also bound the total update of WT. And then afterwards, we will argue that we have the smoothness around a random point in the network. So that's the plan. So F is C Lipschitz and beta smooth. And so for a network, it's very easy to be Lipschitz in the parameters. Because the output of the parameter, there is 1 over square root of the width in the front of the function. Like we want the outputs to be on the random input to be of 1 independent from the width. So that's how we rescale the output. And so this 1 over square root width makes it really Lipschitz for even very small c. And so we don't train the output weight, but still they're all under the square root. And then beta smoothness of the network is true. So here is, I mean, as function of the weights. And so it is beta smooth very smooth for the same reasons. So Hessian also is pretty small. Yeah. Okay. So beta smooth. Now we assume for now that the PL conditions are satisfied. If LW equals to 1/2 minus y squared, satisfied. Now condition. And then here we have around the start point. So here is the ball around the start point of parameter. Then we have 2c over mu times f of w minus y. So if PL condition is satisfied, then gradient descent with eta smaller than 1 over c squared plus beta square root n wf 0 minus y satisfies. So the same exponential convergence. So L of WT smaller than 1 minus eta mu to the power t times L of W0. Okay, well, this is nice theorem. And so now we what we basically say is that the weights will remain inside this ball. one evaluation is satisfied. Okay. I will add it to the theorem because it's kind of important for generalization error. WT and this about S. So and why mu PL condition is satisfied. So so the at this point we cannot tell it. We will need to so I will explain this later. So, but I can tell you what is the idea. We already said it, why mu PL condition. We will prove that in a random point, the min eigen, so PL condition, so is satisfied in the point WT if mu is bigger than min eigenvalue of NTK. We will prove it. It's pretty easy to prove. And then we will argue that in a random point, min eigenvalue of NTK is bounded away by 0. And if we stay in this ball S, then we know the same story. Hessian is small, and so gradients change little, so NTK changes little. But this is still a big work after we prove this theorem. Okay, so now we do this part. And so I will add it in the notes as well, explicitly say that weight vector stays in this ball. Okay, so now we have so first let us see that when we use square loss, so we will first show that if we believe that W stays in the ball S, then the condition of this proposition are satisfied. So the previous result. So what we need is 1 over eta smoothness. And so we will prove that Hessian of loss function is bounded by this thing. And this should now be an easy exercise after all our experience from previous lecture, where we calculate Hessian of loss function. And so we said that Hessian, let me remove it because I will need all the space for this. So Hessian of loss function is equal to, and so I forgot about transpose. Plus, and then we have a sum. Hopefully I wrote it somewhere. No, this is not NTK, because in NTK we have the transpose here. And then we have I smaller than N, FW minus Y times HFI of W. So this was expression for NTK, and now we can understand, right, that we need to prove that 2 norm of HF of W is smaller than what is here. And so, or let us just multiply by unit vector. I guess it helps. And so, so we know that F is C Lipschitz. So when we take Jacobian, when we multiply Jacobian by let's do it like this. So this is bounded by norm of df of W times V squared. And so by definition of being C Lipschitz, so this is bounded by, so W is, V is unit vector, let's say. So then this is bounded by C squared by being Lipschitz, right? So if you take a small change, then this is clear. So plus, and then we need to bound the second term. And here we bound, so the one norm. You already see how you can finish. And here we have, so the maximum over I of. And so here I will use the two norms, I guess. So I need to centrage by V. Yeah, so I have the two norm here. And so now we use that, we have beta smoothness. So this is bounded by beta. So we have C squared plus, and then we have one norm FW minus Y. This is the boring part, times beta. But we use one norm here. So when we go to the two norm, we have a square root of n. So we have that one norm of a vector W. No, that's not. One norm is bounded by square root n of the two norm. So it's Cauchy-Schwarz inequality with the vector containing all ones. Okay, well now we have understand that our function, our loss is 1 over eta smooth. So loss is 1 over eta smooth, Hessian is bounded by 1 over eta, which is this expression here. So that's this thing. Okay, so when we want to apply, we already know that this is okay. PL condition will be okay after we prove that we stay inside the set S. Because we assume mu PL condition is satisfied. So our last task is to prove that in each gradient descent step, we stay inside this ball. Okay. So now I will carefully follow the proof of the notes, and then explanations will be smoother. How far can I go? No, okay. We need to prove that for each step, WS minus W0 smaller than 2C over mu left of W minus Y. Okay. So we will assume that L is eta smooth. Well, I said that it follows from this thing, but there is a small hiccup. We only know that, so we need that L is eta smooth in the lines between the update, but this F is changing here. We don't have fixed W. So we need to guarantee that it's only eta smooth after we know that this norm is decreasing on a line. And so this is very technical thing to do. And so there is a long footnote to prove that it decreases, but it's kind of easy to understand. So Yeah, so I thought it's obvious, and in Balkan paper, they don't write about it. But then when I was carefully writing it some time ago, I realized that it's not at all obvious. I think actually some student complained and say, how do you do this? Okay. So, but for now, let us assume that we have eta smoothness inside this ball. First, I will bound f of wt minus y. So we can write this in terms of the loss, and we know that the loss decreases exponentially fast. So this is bounded by 1 minus Okay, so we are back. I don't know how long I was away. When is the first complaint? Oh, no complaints. So yeah, so it's good to see there are 4 people now on Zoom. Yeah, so what I say is that we will use induction. So up to step T, we assume that we are in the ball, in this ball. And now let's check that we are on step T plus 1, we are still inside the ball. So up to step T, we can assume exponential decrease here. But we have Wt over 2, and we need to multiply by 2 over Lw0. And so this is equal to, so this is bounded, so this is equal to 1 minus mu eta to the power t over 2 times f of w0 minus 1. So we turn back like this. Okay, and now this is good news. So, oh, before I put everything together, so this is observation 1. Let's make a second observation. So let us look to the sum of these coefficients over t. So 1 minus mu eta t over 2. So this is geometric sequence. So from 1 to s. So this is bounded by 1 over 1 minus square root 1 minus over eta. And now you can make some calculation and observe that this is bounded by 2 times mu over eta. Okay. And now we can bound how far we are. How far is WS from W0 is bounded by some WT plus 1 minus, so triangle inequality. I need the third observation, but it's hopefully easier one. And where we have some space. Let's go in the middle. So I claim that gradient of L of WT, the norm of gradient, so the 2 norm, is bounded by eta C f of WT minus y. Okay, so let us understand why this is true. Oh, good question. Oh, sorry, no theta here. No, this should be clear, right? So the gradient of L. So gradient of L, what is it? So that we have squared norm. So it is this thing times gradient of F. And gradient of F norm is at most C. Because if we multiply with a unit vector in the same direction. So okay, this is observation 3. So we know that this is proportional to eta times the gradient. So this is bounded by eta times C times norm of precisely what we started computing here. Sum t equal 1 to S of norm gradient over L of WT. Okay, now bounded by eta over C. Oh no, I already wrote C. Eta times C, sum of f of WT minus y. And then we know that this is bounded by this thing here. W0 minus y, sum of 1 minus mu eta to the power e. And so this sum is bounded by eta over c, 1 over mu eta. Sorry, 2 over mu eta. And so eta cancels. And so it is just 2c over. Oh, and I dropped the FW0 minus y. Okay, and this is precisely 2c over mu times the t. So this is precisely the radius of the ball we considered here. So we know that after the update, the weight vector is still inside this ball. So this is and it means that we finished the proof of this theorem. So we just took 1 over eta smoothness for granted if we believe this subtle point, which we get if we believe that this is always decreasing. which is kind of the whole point of gradient descent, but we still need to prove it. And so everyone thinks it's obvious, but it turns out to be quite subtle. But let's not worry about this. So it's kind of recursive. To prove that this decreases, we need to have some kind of PL condition. Sorry, to prove that this decreases, we need 1 over eta smoothness, but that uses that this is decreases. So that's why the trouble appears. So eta, but then you can look like, okay, let's assume it's decreasing in some open set, and then prove that's both open and closed, and then we understand that there cannot be a last point where f of w minus y is no longer decreasing. So basically the proof say, okay, let's look into little steps on the line, and let us look to the last step where we are increasing. And if it starts decreasing, okay, then, yeah, I don't know how to say, but it's like, just a proof that there cannot be a last point where it is stable. Okay, anyway, so I will never bother you with the question why this 1 over eta smoothness is happening. And so if we believe in this, then we know we have 1 over eta smoothness, and we have PL condition, because we assume that in the ball, and we recursively show that we stay in the ball. And so, so once we are in the ball, we can prove that we stay in the ball. It doesn't seem convincing from the face, so let me check where is the issue. Okay, so I've been not so good with the parameters should go to s minus 1. Okay, so I get so faces are not happy. So somewhere something is wrong. So so the point is that we are good as long as we are we are up to s minus 1 by the induction hypothesis. But then there is a last step where we have the vector ws minus w s minus 1. Okay, and then we should think about this proof again. So here, so here we use the PL conditions, but we use one PL condition less. And so when we have trajectory of W, so here we have t plus 1. So to have this exponential decrease, we only need the PL condition in the previous points in this proof. So here I kind of say it for all t, but here it would be like if this is true for all t strictly less than s, then we have like this. Because in the proof, we remember the proof, we wrote linear extrapolation, but it was in the previous point of gradient descent. And then we proved the bound on the next point. So I should have stated it more carefully. That's probably the reason of unhappy. Hopefully that is the reason of unhappiness. So, so we know that if we have PL condition for t strictly smaller than s, we have the bound on one more s. And this is what we are using here. So by induction, we assume that we are okay in strictly smaller than s. But then at the next update, when we go to WS, we are still good. And because in the maximal value, we have WS here. So in this the last gradient we use here, W, okay. Yeah, and so the last task, we prove that we stay inside this bar. Okay, and now we are almost in the end of the lecture notes. So there is just page the end. I already explained what is tangent kernel. So let us think a little bit about tangent kernel of neural net. So, well, this is not about neural net, it's about general systems. So there is there exists algorithm to solve linear systems by using gradient descent. Sometimes it works very well. So you want to solve quadratic equations. So you receive a set of points. So let me so let us have f. Let us consider yeah. Of W equal to X times W. So here X is a matrix that has the data points in rows. And so you want to, yeah. So here we assume that X1 till Xn is element of Rm. And here we have X equal to X1 till Xn. Right, so there are rows, and we want to find. So we are given a vector y, and we want to find xw minus squared equal to 0. And so we want to solve linear system, and one way to do it is following gradient descent. And so how fast will it work? Will you only need a logarithmic number of iterations, provided that X is suitable matrix for this approach. And so what this theorem that we had before, I just deleted it. This theorem gives us a criterion. So we can use previous theorem to indeed understand for which X this will work very well. And so for this, we understand, we want to prove, oh, for some reason I didn't say. Oh, I forgot to tell something important. What is the tangent kernel? So what do I say? Oh, here. Yeah. Okay. I'm explaining things in the wrong order. I start with an example, but we still didn't connect PL condition to. Okay. I didn't say what is tangent kernel, so I'm sorry for confusion. So there is your question, why is PL condition satisfied in neural net? And so let us have a definition. Tangent bet marker. So tangent kernel is of f. So it's written like K of f of W is equal to df. And so the thing that we've already seen before in the beginning of the lecture, transpose. So this is called tangent kernel. And so there is a little lemma. L of W for the squared loss. We have that 1/2 gradient L of W squared. So gradient is bigger than the minimum eigenvalue of Kf of W. So this is our lemma. And you probably kind of guessed it, that is true before. So for the square ones. And so do you remember why this is true? Should I prove it, or it's okay? It's pretty short. I just need to write what is the gradient of L. Okay. No, it's really short. I should do so. Let us say that V is equal to F of W minus Y. And then we have that gradient of L of W is equal to dF of W transpose times V. So this we already seen, and then WL of W transposed, so gradient of L of W is equal to V dF times dF transposed V. Yes, here should be transposed. Right, and this is the tangent kernel. dk of WF V. So yeah, so this we already did. Okay, so now what is this? Let us have some feel for this tangent kernel when we solve the thing that I started to explain before. We want to solve linear system using gradient descent. And so tangent kernel Kf of W, well, it doesn't depend on W because we have linear system when we take gradient. So when we take gradient of F, W falls out. When we take Jacobian, yeah. So Jacobian will just be X. So the tangent kernel is X times X transpose. So in our theorem, we had two conditions. So this PL condition has to be large, but also we need eta smoothness. So we need to check the Hessian. And so Hessian of linear system will be, so what is Hessian of the loss? We need the Hessian of the loss of W. So what is it? So we had a formula, remember? There were some D's and then there were Hessians of F. But Hessians of F were, so there were two terms, right? But the Hessians of F, they are zero because we have linear function. So the L was equal to, and then we had the opposite of NTK. And so we had DFT. So we have XT times X. So we, to get eta smoothness, we need to look to the maximum eigenvalue of Hessian. But for PL condition, we need the minimum eigenvalue of Kf. And so there is a little theorem that says, so if we have a matrix, so we have a matrix of the form x(xt) and of xt and x here. And so there is a little exercise in linear algebra that says that these two matrices have the same non-zero eigenvalues. And that means that we can just look at a single one of these matrices. So if we assume that here the min eigenvalue is non-zero, then we know that, so we can apply gradient descent, but with eta equal to 1 over max eigenvalue of xtx, or let's just say af. And the PL condition is satisfied by a minimum or minimum of eigenvalue condition. So if we choose gradient well, then the convergence that we have, so the product of mu and eta times mu is called a condition number. So the like kappa of kf. Condition number is, I hope I remember correctly, min divided by max eigenvalue, or the opposite. I think it's the opposite. So, sorry, max. So condition number kappa of kf is max eigenvalue divided by min eigenvalue. So if this matrix has good condition number, then this technique of solving linear system with gradient descent goes very well. And there is something interesting about condition number. When you take random inputs, so when we create a random matrix, so you take all entries of matrix independent Gaussians. So if X is matrix n times m, right? So all the inputs are rows, and we take input size m number of parameters. So then condition number k of x, so all independent normal entries. Then expected value of condition number is equal to m divided by m minus n plus 1. So there is theoretical result. Actually, there's only 1/2 of this result. So for small m, this was known for many years. For big M, so Belkin proved it recently. And so here, so this condition number, so this condition number is small, reasonably small, if either m is very large or m is very small. Then this condition number is small. And this is precisely explains, so okay, I can take a leap, but precisely the same mathematics can also explain in a pretty precise way double descent event. So when m is proportional to n, then test error suddenly goes up and some overfitting takes place. But then when n further decreases, and often it's even better. When m becomes even larger, then it becomes more stable. And so here, this is just a silly example with linear things, but it's the same mathematics that computes this expected value that explains why there is a peak here. There is a certain singularity in the input matrix. So there is a gram. So the eigenvalues are connected to gram matrix. Okay, I cannot explain it. It's just a little bit. Like I need 2 or 3 lectures to go through the mathematics of this. But it just, this example is kind of more than just an example of a linear system. Okay, so now we should say a little bit, what is NTK? Oh, but it's also time to finish the lecture. So there is still a page 8 and 9 in the lecture notes, where there is a discussion of minimum eigenvalue of NTK. So in order to apply this, we need PL condition to be satisfied. We need, in other words, we need to bound minimum eigenvalue of NTK when in a random point W0. And so to explain this completely, to prove this completely, it's not possible. So I will just outline this and then we will finish the lecture and the course. So what's the idea is to prove that if we have a neural net with one hidden layer, then NTK is related to Gram matrix of the training set. So we don't have exact equality, but what we have is that NTK is 1/4 of this matrix plus something else. And so there exists a theorem that says that Gram matrix always has positive eigenvalues if and only if no two inputs are parallel. So if two inputs are parallel, then yeah, it's kind of easy to understand what will happen in neural network. So this is for ReLU activation in the hidden layer. So in ReLU activation, when you take random input vector, so what are we interested in maximum of 0 and x times w. And so this is basically multiplying a point x with a random w when we initialize. And so with probability 1/2, this will be 0. And with probability 1/2, we compute a random linear function. So then in the last layer, we consider just whatever activation we want, but it's kind of one Lipschitz. And that's what I want to say. So I want to say why NTK. Well, the only way is that okay, so when we look to the gradient, we can basically ignore what's happening in the output neuron. And well, just calculate it and see that it is basically such a Gram matrix. So when we have a very wide network, it will converge to this thing here. And so yeah, I could just go through the calculation, but okay, why not? So so let us consider a point x alpha. So then what is the gradient? So kernel is n by n matrix. And so it is, where is the definition here? And so when we take the alpha beta entry of this matrix, we're basically multiplying the gradient in alpha, in input alpha and input beta. Okay, is gradient of fx w alpha times gradient of fx w beta. Sorry, x alpha of w times x beta of w. Okay. And now we need to check what is this gradient for real. So let me write function. So we have f of x w equal to 1 over square root k sum over max x times w I equal 1 to k. And here I break w. So I say that w is kind of matrix. Maybe I should write capital W. So W is matrix of size k times d. So W, and so here we have and I forgot maximum of 0 and this thing. So when I take the gradient to W I, so it will be equal to sum over. So if this thing is negative, then when we take derivative to corresponding vector Wi, it will be 0. And so we have to check in the sum. Oh, I forgot the 1 over k. 1 over square root k. So we check whether x alpha times Wi is bigger than 0. So there is indicator. And then we multiply by x alpha. This will be the gradient. And then we do the same for xb. xb, and we need to multiply by vector xb times w bigger than 0. So, but you already did this in previous seminar. I think I added to the list, but in the bottom of the list. So probably you didn't get there, or I don't know. I don't know. We didn't see the definition yet, so I guess it was not in the seminar. Anyway, so here is the so NTK for one layer neural net with linear output neuron is equal to this thing here. So here we have dot product of x alpha and x beta. So it reminds us about Gram matrix, which we had here. It's the same thing, but here we have a lot of random vectors. And so each of them is bigger than 0, it's probability 1/4. So that's why, and so NTK now is exactly equal to, okay, but no, it's not true. So, but they're not independent, that's my mistake. So if x alpha and x beta are orthogonal, we would have 1/4 here. But if they are aligned, it's only 1/2. And so there is a nice formula with arc cosinus between these two vectors. But this arc cosinus can be proven to be bounded by by dot product divided by 4. Okay, and so after all this, we get bound on eigenvalues of NTK from Gram matrix. So if we believe our vectors are randomly generated, then we can get some old paper that say Gram matrix has positive eigenvalues if no two input vectors are parallel. Okay, and so this is a long story to explain why in random point PL condition is satisfied. And then we have to apply one last lemma that says that if we stay inside this ball, if we move in the ball of 1 so of one something independent from the width of the network, then eigenvalue stays bounded away from zero. But this is similar like we did in the beginning of the lecture when we proved that gradients are stable. We can also prove that min eigenvalue of NTK is stable because NTK is built from gradients. So this is just on the last page of the notes. I don't ask it on colloquium. It's easy to believe. So I propose that we stop the lecture here. So there is no seminar today. I forgot to tell. Yeah. So, okay. This is everything I had to tell. So I will put more references in the notes, and in the beginning of the lecture, I explained about a simple way if we believed in linear net to linear approximation that we have exponential decrease. So this is the basic story. All of this with PL condition is because our net is not linear and we need to deal with it. Okay, so finally, I repeat once more that since we now know that we stay inside this ball, we can use generalization bound for this ball. And we know that if W, so the generalization, but we had Rademacher complexity bounded by, so there was the class of functions, x goes to W times x, so the dot product, and the norm of W is bounded by some B. So, and we proved that this Rademacher complexity was bounded by B times R square root n, where R is the norm of X. So the norm of the max norm of input. And so precisely the same bound on Rademacher complexity also applies for functions of the form X go to, and so functions of the form X go to W0 plus W times X. So this is precisely the same bound. We can just check it on definition of Rademacher complexity, that if we add something, or maybe one needs to, okay. So it turns out that precisely the same proof that we had for this bound applies to this bound where W0 is fixed. And so this explains why we have good generalization. It is because Rademacher complexity does not depend on the width, provided the width is large enough. And so this finishes the whole story for neural nets. Okay, so, and this finishes the course. So to add something about neural nets is kind of pushing the limits of what I can put in the course. But the colloquium is just to prove this theorem and this theorem, which is a part of it. Okay, so now I really finished speaking. And so you are free until next week, yeah, when there is colloquium. Okay, I have a little quiz, but there is the same question of last time. So I was in a hurry to finish to create a quiz before the lecture. Here it is. So just 2 questions. Okay. So now you are free. Now you know the best theory I am aware of for generalization of neural nets. So
Okay, can
Yeah.
I ask you a question?
Yeah.
Like about the proofs, like here. So, why do we look at the case where this is like this equation is false?
We make mistake bound. Um, that all. Sorry. Um, so, what was the first observation?
Um, what-
Yeah, so there was the pre. Can I scroll
sure.
up?
There's just like a different.
Yeah. So what I want to say is that we just need to change A for the case that this is not true.
Okay.
Um, yeah, I just say that that's what I wanted to say, but maybe I say it wrongly. I'd say that there is just one case where this inequality is not enough. Like if we want to copy the previous proof. Yeah. This was assumed in the previous proof.
Okay.
Yeah. But now we can no longer assume it.
Okay.
Yeah. Then it's logical. Yeah.
Thank you.
Yeah. Yes.
The exam date,
Sorry.
exam dates.
No, I cannot find. Do you also you don't have? I will go to administration now. So, well, no, I will first put the quiz grader and then yeah, yeah. Goodbye. Should